Dear ones, welcome back to the Engineering Geology class series, Module 4. Now we are discussing Part 3, that is quality aspects and exploration methods for groundwater. So, dear friends, we all know that we have very less quantity of fresh water, that is only 2.5 percentage, and in this 2.5 percentage of water, bulk part is locked up in the polar ice caps, or it is trapped in ground surface or subsurface. So the accessible water is very less, and we well know that the water can be misplaced and it can be polluted, possibly beyond our abilities to purify it. Whether the world has enough water fit for drinking depends on how much it is available and where it is available, how much we use, and its quality. In the industrialized countries, the threat to the quality of the water is of prime importance. In the third world, it is the scarcity of the water as the key factor. According to WHO, WHO has been estimated that more than 60% of the people in the developing countries did not have enough water. Between 9 to 22 million children less than 5 years old die each year just because of lack of good quality water or inadequate sanitary facilities and waterborne diseases. Ironically, reservoirs, irrigation and drainage system, as well as inadequate separation of drinking water and waste disposal system, is the way for the diseases. Though the fulfilling demand is not difficult, keeping the water pure is a very difficult problem. The wastewater which joins the rivers, oceans, contains pollutants, and those generated by mining and metal industry, paper industry, petrochemical industry are particularly damaging the rivers, lakes, canals, and oceans. Dear friends, we know that in this context there is a great import. Government of India is giving a greater importance to the quality over uh, since last 4 years, due to the increasing reliance on the water and the realization that once contaminated it is difficult and it is highly expensive and sometimes impossible to restore the natural resource and its original state. The chemical, physical, and biological parameters determine the usefulness of the water for various purposes. Moreover, hydrogeochemical studies give an important indication on the enclosing lithology, velocity, and direction of the water movement. Thus, it is now generally recognized that the quality of the groundwater is just as important as its quality. The quality of water is judged on the availability of the good water. Okay. So the ability of the water to dissolve minerals determines the chemical nature of the groundwater. The concentration and composition of the soluble salts in water determines its quality for drinking and irrigation. The major constituents in the water occurs mainly in ionic form, like Na plus, K plus, Ca plus, chloride, HCO3, and sulfate. These minerals comprises more than 90% of dissolved solids. And in this chapter, we are discussing only 4 basic criteria for evaluating water quality for irrigation and drinking purposes. These are total hardness, water salinity or water conductivity, sodium hazard, it's also known as sodium absorption ratio, and sodium residual sodium carbonate content. Let us discuss one by one. So sodium adsorption ratio. It's a measure of suitability of the water for use in agricultural irrigation, and it is determined by the concentration of the solids dissolved in the water. It is also a measure of the sodicity of the soil as determined from analysis of water extracted from the soil. Uh, uh, the sodium adsorption ratio can be calculated by this formula, Na divided by a square root of Ca plus Mg divided by 2. So here all the values are expressed in equivalent per million. So although sodium adsorption ratio is the only one factor in determining the suitability of the water for irrigation, in general, the higher the sodium adsorption ratio, the less suitable the water is for irrigation. Irrigation using water with very high sodium adsorption ratio may require soil amendments to prevent long-term damage to the soil. So it disturbs the tilth of the soil, thereby affecting the yield. And also the sodium adsorption, high sodium adsorption ratio will decrease the soil moisture, or it will lead to soil moisture loss, and it will decrease the tilth. This will also lead to the decrease in infiltration and permeability of the soil, by leading the problems for the crop or crop generation. Okay. So sodium hazard, there are 4 classes: C1, C2, C3, C4. In first class or C1 class, the SAR limit is 0 to 10. It gives the water samples, or the water having SAR 0 to 10 is of excellent quality. There is very little hazard, or hazard is sodium hazard is nil. C2 class 10 to 18, it's a water, the SAR value, if the SAR value of a given sample is 10 to 18, the water is good and it is appreciable hazard, but it can be used with appropriate management. So the third class is C3. Here the SAR value is 18 to 26 EPM. It's doubtful. The quality of the water is doubtful here. It is not at all good for most of the crops. And C4, it's unsuitable. One should not irrigate any crop or any field using C4 class of SAR. So then let's go for residual sodium carbonate. It's also known as Eaton's index. Residual sodium carbonate is the index of irrigation water or soil which has been used to indicate the alkalinity hazard for the soil. The RSC index is used to find suitability of the water for irrigation in clay soils which have a very high cation exchange capacity. When the dissolved sodium in comparison with dissolved calcium and magnesium content very high in water, the clay soil will swell and it undergoes dispersion, which drastically reduces the infiltration capacity. The pore spaces in the clays have been reduced, thereby the infiltration capacity will get reduced, and it will lead to less permeability, transmissivity, and the storage capacity, etc. So RSA is calculated by analyzing the HCO3 and CO3 ions in given soil and the Ca plus magnesium ions. So this table gives the index of RSC. If the RSC or residual sodium carbonate is less than 1.25 milligram per liter or milliequivalent per liter, then it is a very good quality water. If the RSC is in between 1.5 to 2.5, the quality is doubtful. It should be treated and then it is used for irrigation. If it is more than 2.5 MEQ per liter, then it's not at all suitable for the irrigation purpose, and it can't be treated. Even though it is treated, then also you can't use this water. So in the dispersed soil structure, the plant roots are unable to spread deeper in the soil due to lack of the moisture. However, the higher RSC index water does not enhance the osmotic pressure to impede the offtake of the water by the plant roots, unlike high salinity water. Clay soils irrigation with high RSC index water needs to follow alkali soil formation. That is not at all good for any crop. It will lead to the salinization patches. So then total hardness. So there are mainly two types of hardness in any given water, especially water from hard rock terrain. That is temporary hardness and permanent hardness. Temporary hardness is due to the presence of bicarbonates of calcium and magnesium. So whereas the permanent hardness is due to the presence of chlorides and sulfates of calcium and magnesium. The temporary hardness can be removed very easily by means of boiling. When the temporary hard water is boiled, the carbonates decompose with liberation of carbon dioxide, and the precipitation of the insoluble carbonates is formed. Whenever you take hard water or water from hard rock terrain, if you boil it, you can see that precipitation, white powdery like precipitation in the water after the boiling. That is nothing but the insoluble carbonate which has been precipitated. So permanent hardness, as we already discussed, it is due to the presence of chlorides and sulfates of the calcium as well the magnesium. These salts do not decompose on boiling. So permanent hardness cannot be treated or removed easily. It can be removed by special processes like lime treatment, when MgSO4 is responsible for the hardness. The total permanent water hardness is calculated with the formula total permanent hardness is equal to calcium hardness plus magnesium hardness. So the calcium and magnesium hardness is the concentration of calcium and magnesium ions expressed as equivalent of calcium carbonate. Hard drinking water may have moderate health effects, but they can pose very serious problems in industrial settings where the water hardness is monitored to avoid costly breakdowns in boilers, cooling towers, and other equipments that handles the water. In domestic settings, the hard water is often indicated by a lack of surge information or surge formation. So then, when soap is agitated in water, and it will give a less lather. Okay, so whatever the water hardness is a great concern, water softening is commonly used to reduce the hardness of the water. So hardness of the water is always expressed in milligrams per liter or ppm. So if you have 0 to 75 milligrams per liter in a given water sample, then that water is considered as very soft water. And if it is between 75 to 155 mg per liter, then moderately hard. 155 to 100, it is hard. It's more than 300, the water is considered as very hard water. So this is all about determination of quality aspect according to the syllabus. Uh, Now let us go for different methods of groundwater exploration. Here the objective of the groundwater exploration is to study and understand the hydrological cycle of a region and to have an overall concept about the type, nature and number of aquifers and the quality of the groundwater. Usually the groundwater exploration projects pass through the phases to uh, reach these objectives by regional surveys, detailed surveys, and exploitation of groundwater by means of boreholes and wells. So here are some methods and techniques which has been used for groundwater exploration. So there are mainly we can categorize these methods into three headings, that is aerial uh, groundwater exploration methods, surface exploration method, and subsurface exploration method. So in aerial exploration method we have photogeology and remote sensing and GIS. Surface methods, geological and geophysical methods. Subsurface method includes test drilling and geophysical logging. Of these, all these methods, geophysical methods are most popular methods. So geophysical techniques in or investigations are conducted on the surface of the earth to explore the groundwater resources by observing some of the physical parameters of the geological formations or the aquifers, like density, velocity, conductivity, resistivity, magnetic susceptibility, electromagnetic and radioactive phenomenon. So geophysical methods comprise the measurement of signals from natural or induced phenomenon of physical properties of the subsurface formations. Geophysical methods detect the differences or the anomalies of these physical properties like density, velocity, electrical conductivity, resistivity, magnetic susceptibility, radioactive phenomena of the earth's crust or geological formation. All these geophysical techniques, there are different types of geological techniques: self-potential method, electrical resistivity method, telluric, magneto-telluric resistivity method, induced polarization, chargeability method, electromagnetic conductivity method, etc. The electrical resistivity method is the most popular method. Let us see. So let's go for electrical methods. These methods play an important role in aquifer zone delineation and as well the groundwater exploration. This technology is economically much viable, and the analysis is not that much complicated as in aerial techniques like remote sensing and GIS. Mainly two electrical methods are there: self-potential method and electrical resistivity method. These are the two methods we are much interested. Self-potential method here this is the only electrical method which uses the natural current. The it measures the voltage in millivolts. Here in SP method, SP potential or self-potential measurement analysis and interpretation throw light on the movement and streaming of groundwater. So that is transmissivity of the groundwater. This limits the area of interest for further surveys and investigations. So SP measurement, in SP measurement techniques are two methods: gradient method and total field method. So here the electrode configuration is like this. It is fixed electrode spacing, whereas in total field method, fixed base will be there, and this picture shows the electrode configuration. Then this electrical resistivity method is the most popular method amongst all the geophysical method or the groundwater exploration method. This method is one of the most important and effective techniques to decipher the nature of the subsurface geological formation, in turn to know the subsurface hydrogeological condition. The resistivity is the best physical parameter that characterizes the hard and compact rock from the weathered and fractured horizons. The water content in the pores of or fractures or joints of the rock formations brings down the electrical resistivity considerably, or the electrical conductivity will be more here. This resistivity variation is used to differentiate between water bearing and non-water bearing formation, that is aquifer or aquifuge, aquitard or aquiclude. So principles of electrical resistivity methods are the electrical resistance is a very much physical property of material, and it is independent of its size and shape. It is defined as the resistance offered by a unit length of substance of a unit area to flow the electrical current when the voltage is applied across the opposite phases. The resistance and further resistivity is calculated by using the equations, that is using Ohm's law. The resistance have been calculated. R is equal to P by I, or rho is equal to R into A by L. So measurement of the earth resistivity, it involves the application of 4 electrode systems. One pair of outer electrode serves as the electric current, or it introduces the electric current into the ground, while the other inner pair measures the potential difference produced as a result of current. There are two types of field procedures. Okay, so two types of investigation will be there. Resistivity profiling, it deciphers the horizontal variation, that is you can know the areal extent of the aquifer, whereas vertical electrical sounding or VES deciphers electrically downward variation. How much depth a aquifer is determined by vertical electrical sounding. So there are mainly two types of electrical electrode arrays will be there, or electrode arrangements. First one is Venner arrangement, and second one is Schlumberger arrangement. In this Venner array or Venner arrangement of electrodes, it consists of 4 collinear equally spaced electrodes. The outer two electrodes are typically the current or source electrodes, and the inner two electrodes are the potential or the receiver electrodes. This picture clearly explains the electrode configuration. Then second one is Schlumberger array. This is an array where 4 electrodes are placed in a line around a common base point. The two outer electrodes A and B are current electrodes, and the inner electrodes are potential electrodes. And compared to the outer electrodes or current electrodes, these potential electrodes are placed close together. So acquisition of electrical resistivity data. The area around center point of investigation must be plain, and it should be free from artificial dumps, overhead power cables, and underground pipelines or communication cables. The orientation of the sounding is fixed by observing the topography and the parallel local strike of the formation, so that all 4 electrodes fall in the same formation or on the same aquifer throughout the sounding. So when we get the data by electrical sounding or electrical resistivity method, we have to process it. The processing and analysis of the field data to get geoelectrical parameters in terms of resistivity and thickness. Using these parameters, one can infer the nature of the subsurface formation on the basis of geological knowledge and his interpretation capacity and correlative studies. There are mainly two types of analysis and interpretation techniques, that is qualitative techniques and quantitative techniques. Quantitative analysis of electrical resistivity survey includes curve matching technique or inverse method, and inverse slope method or direct method, and third one is strip method of interpretation. Of these three quantitative analysis methods, curve matching technique is the most popular method, This curve matching technique is prominently used for three layered formations, where we have model curves, and the curve obtained by the field data has been matched with the given prototype or model curves. There are mainly four types of curves: type H, type A, and type K, and type Q. In type H, the resistivity of the first layer is greater than the second layer, and this third layer is having the greater resistivity than the second layer. So it means this second layer is having, or it is having an aquifer which is having a very good quantity of water which is in exploitable limit. So type A in the same way expresses the layer 1 is having lesser resistivity than layer 2, and layer 2 is having lesser resistivity than layer 3. So it means the layer 1 is the potential layer of groundwater exploration. Same way the type K, rho 1 is less than rho 2, and rho 3 is also less than rho 2. And type Q, here rho 1 is greater than rho 2, rho 2 is once again greater than rho 3. So first layer is highly having very high resistivity and having very low conductivity, means rho 3 is having very good quality or very good quantity of water. So electrical resistivity for different rock formations is given here. Quartzite, weathered rock quartzites rock formations are having resistivity ranges between 4.4 to 2, and granites, like sandstone and limestones, are very good aquifer zones. It has been given here, and clays are being non-permeable or non-porous or impermeable, or having very low or high resistivity ranges, and though they won't yield very good quantity of water, they are not at all good aquifer zones. Oh, this is the machine or electrical resistivity meter used for the electrical resistivity analysis. So then let us move for one more technique, that is seismic method. Seismic methods contains mainly two types of methods: seismic reflection and seismic refraction method. Seismic reflection methods provide information of geological structure thousands of meter below the surface, that is deep seated strata can be analyzed or explored using seismic reflection method. In seismic refraction method is of interest in groundwater studies go only about hundreds of meter deep, or only a less depth or less deep formations can be explored by this method. Seismic refraction is a geophysical principle governed by the Snell's law, of refraction. The seismic refraction methods utilizes the refraction of seismic waves by the rocks or soil layers to characterize the subsurface geological conditions and geological structures. Here the travel time of seismic waves depends on the media through which it is passing through. The velocities are the greatest or great in solid igneous rocks, and it is very least in unconsolidated material. This phenomenon have been used in seismic refraction method. So based on these indications, it is possible to delineate the subsurface zones or aquifers or zones of fractures, fissures, faults and lineaments, analyzing seismic velocities. A basic understanding of characteristic of seismic velocities for a variety of geological materials is necessary, and it is the groundwater exploration, especially in hard rock terrain and even in alluvium also. So these velocities help to identify the nature of the alluvium or the bedrock. In coarse alluvium terrain, seismic velocity increases markedly from unsaturated to saturated zone. So this is all about different types of groundwater exploration methods, that is electrical resistivity method and seismic diffraction method. And let us discuss part 4 module in coming classes. Till then, goodbye. Thank you.